Okay, great. My name is Tom Akuch. I'm a solution engineer with Hortonworks, and here with me today is Oleg Zurkowski.
Yep, that's correct.
Principal architect from our professional services team. We're going to be talking to you today about high-speed, continuous, reliable ingest.
And smart.
And smart.
Yeah.
Well, smart is implied, I guess.
Yeah, that was added later, but yeah.
Why would you do it any other way? So we have been working together at a fairly large opportunity, a use case within the telecommunications space to ingest a large amount of concurrent call detail records. So this talk kind of has evolved out of our experiences, delivering that project. So just a quick note on the agenda. We're going to kind of open up with the domain problem. I think you're all very aware, but ingest is commonly overlooked, right? It's something that we normally just take for granted, right? We haven't really spent a lot of time, or had to spend a lot of time recently around, optimizing the problem of ingest. But new data types are kind of pushing the limits of what we can do with hardware, and we need to think about the problem of ingest as a result. So this talk will be focused in on that. We're going to talk about how Hadoop is being commonly used within event sourcing solutions and why it's a good fit there. Then we're going to get into kind of the bits and bytes, and Oleg is going to take over and walk you through kind of our process for solving the problem of high-speed ingest.
All right, and I just want to add something that you said, you mentioned the new data types. It's not only about the new data types, it's the new sources of data. If you look at the evolution of the Hadoop, it was more of initially a pull model. Send the crawler, crawl the web, gather HTML pages, and send them over for analysis. Well, in this case, we're getting into the sources that actually push data into HDFS, and now we have to deal with the fact that the rate of data production that we can digest, and we have to start innovating in this space to be able to support the high rate of data production.
All right, so let's dive into the domain real quick. All of you are probably familiar with the problem of events, and these are just some of the new data sources that people are looking to flow into Hadoop. We run into this, across all of our customers, across every industry. It's a common thing that people are looking to do with Hadoop. They're looking to these event streams to mine new data out of them, data that was previously really unknown or used only for problem diagnosis. So what they have though is a set of patterns of behavior, patterns of interaction, or a set of observations, patterns of observations that really give people an insight, right, into why customers are choosing to do a transaction with them or not. Right, and that's the power of big data, is to look. We're all very good at managing our transactions today, but understanding the patterns that lead to a transaction, or if you want to, more generally abstract that, an outcome, right, an outcome that we want to drive, then that's where big data comes in, and that's where analyzing event streams is particularly important. So Hadoop makes a great event source solution. Event sourcing has been around for quite a while. And you can see here that not only are there a number of different events that are kind of flowing in a regular fashion into Hadoop, in a continuous fashion, but there's also a number of applications that we need to feed on the way out. And the nice part about Hadoop is that I don't have to, I can land that raw data, right, in Hadoop first, and then think about how I need to process it forward it down to those solutions such as search and analytics and relational databases after I've landed it.
But the goal is to actually land it there quickly.
Yeah. So this talk will focus in on landing it there and landing it there quickly, as Oleg talked about. So streaming sources of data, in particular the one that we kind of came up against, are unique, right? They're unique problems in the IT space. It's very easy to produce them, right? But the most important thing is you want to create a solution that does not impact the producer, right? In order to, as you're collecting these events in real time, you need to be able to keep up with the rate of production, right? That's key. But you want to do that without impacting the current system in any way, and that's very important. Source data is always in motion, right? So from an analytics standpoint, the analytics on this sort of data is very different than what you might do in Hadoop. But there is opportunity to kind of inspect the data as it's flowing through to gain new insight. And obviously, there's a lot of solutions in that area. So there are often more than one streaming source. In our case, we had an individual streaming source producing messages at a sustained rate of 200,000 messages per second. That was one source, right? There were 50 of those in the initial deployment planned.
And each one of them can spike to 400,000 messages per second. So you can.
Right, so that's 10 million sustained messages per second.
That's what we accomplished. So it's probably a higher number than we really needed to.
With
but that's
bursts
what
well above that, right? So, it's very important to devise an architecture that is scalable in a horizontal fashion, much in the way that Hadoop is scalable, right? So you don't want to kind of stick a central, point of bottleneck in front of your cluster. You want to take advantage of the scale-out capabilities, and you also need to consider the fact that events are rather small in size, right? So the events that we were looking at were only 250 bytes, roughly.
Yeah.
So an individual message is not that large, right? So I probably don't want to wake up the elephant every time I want to write 250 bytes, and that's kind of the other piece of knowledge that we'll be talking about as we get into this.
In fact, the Java NIO book, actually there's a quote that I always use. I forgot the name of the author, but he basically says that in the current modern system, expect truckload, and we're still using the old IO style and giving it shovelful. So, and that's essentially kind of the different analogy to the elephant thing. So.
Yeah. So why is Hadoop a good fit for event sourcing? A lot of this is, immediately understandable, right? I mean, events are immutable, right? So I write them, and I might derive different insight from them. That's known as the command and query response segregation pattern. For those who come from like an enterprise Java background. But that query, the way I query those and the information that I gain from that, does not mutate the core message, right? So I keep that raw event, and I'm able to then kind of process over that multiple times, right, to feed different downstream solutions. Their event logs are append only, right? So I'm not going back. I'm not doing, random read write. Right.
That's a big difference with the transactional data, which could actually exist in multiple states and could change. Here, event happened, that's it. There is nothing to change in the event. Otherwise, you break in the major law of, life, I guess.
So event sourcing is not just about storage, right? If I can't process this data and gain new insight into it, then why did I gather it in the first place? We're right back where we started. So you really take advantage of the ability to not only store this data within Hadoop, but process it. You know, data, even though it starts out as 250 bytes in size, when multiplied by 10 million per second, you're going to get fairly large volumes. Roughly over 250 terabytes per day, I think was what we calculated, potentially even higher. And again, you know, event sourcing solutions are ecosystem dependent, right? So, you know, those search solutions and, you know, the analytics solutions, the visualization tools that you see in the marketplace, those are all very important, you know, to kind of complete the cycle and make the data that you're ingesting valuable. And that is another good reason why you want to put it into Hadoop, because Hadoop is built to integrate with all those solutions and integrate well.
All right, so we're going to talk about the ingest mechanics right now, and I'll start right from the demo. And what we're going to do, we won't have enough time to get into the entire solution that we built for this particular client. But what I really want to talk more about is how we as developers can really look at the problem, parse it out in little pieces, figure out where are bottlenecks, and fix the problem before we use the good old throw more hardware at it, right? So what I'm going to do is I'm going to switch to my Eclipse, and actually Spring Source Tool Suite, I came from there, so kind of got used to it. But anyway, so what we're going to do is I'm going to just write a very simple kind of a Java program, and we're going to kind of evolve it throughout this presentation and see what we can accomplish, right? So, but before we begin writing any code, as you can see, this method, I already have the template set up, so that template is basically emulating my source system, and the source system will invoke this method every time there is a message produced, okay? So let's first figure out how fast the messages are produced, because, for example, if the messages are produced at a certain rate, and you want to be able to ingest them at a much higher rate, well, there's nothing you can do because they're not produced that quick, right? So, let's run this just to establish the initial where we at. Go ahead. All the parameters? This is just for the test parameters, but yeah, so I have a byte buffer, I have a byte representing a record, I have a counter, and I have a basically for the data output stream wrapping writer, which exposes the channel so I can write the byte buffer, and then the file output stream for different purposes. It's more for the test, so it's because why would I need a writer and file output stream in the same method? It doesn't make any sense. But again, so as you can see, we're producing 1 million messages just a little over a second. Now, the client gave us an SLA that they want to be able to ingest data at a certain rate. Well, so in this particular exercise, we're just going to pull that SLAs out of the sky. We're going to say that I want to be able to ingest 1 million records within 2 seconds interval, right? So let's see if we can meet that SLA. So what we're going to do is just going to say,
so all we're going to do here is try to write the records as they come in.
As they come, yes. So we can see that a very simple I/O, I mean, you could not make that any simpler than what it is already. And there's no thread that sleeps or anything else. So as you can see, as soon as I start writing it, I'm at about just a little over 3 seconds. So I'm already past my SLA. So not only I'm past my SLAs, you always have to think about that. You don't just want to meet the SLA. You want to really beat it, because you always have to answer the question, what about the growth potential for this system? Okay, like today we have 50 devices. Tomorrow we're going to have 60, 70, and what have you. How much room do I have until I have to start thinking about throwing more hardware at it? So obviously we cannot meet our SLAs, and we have a problem, right? So let's switch back to the presentation and start talking about the problem. So, and the problem is that we, as I said earlier, we do use this, throw more hardware at it. But have we, how do we know that we actually exhausted all available resources within our existing hardware? If I run this process again, I'll do it, actually I should have done it before, right? If I run this process again, just a simple profiling, you understand what that little window that I just pulled out means, right?
That's the CPU utilization?
That's my CPU utilization, right?
You see we're hardly touching CPU.
So I have 8 cores in this machine. And am I using it? Am I using it to help me with the ingest? And one might say, well, how can you use it? I mean, that's an ingest, that's an IO-bound process. That's where we're at. This is why it's slow. This speed represents the speed with which my hard drive can take the data. Well, not exactly, and we're going to address that problem. But at least from this perspective, from the CPU perspective, I can clearly see that my CPU is way underutilized. So which means until I go to my management, ask for a new laptop, I should probably figure out if I can fix something within the current resources because I'm not using them. So, and this is what I come up with this slide, which is basically I look at the computer in a more sort of a general way of these four musketeers, Athos, Porthos, Aramis, and D'Artagnan. So basically we have the memory, we have hard drive, we have disk, we have a network card, and we have CPU. So, and what the goal was to say, listen, within our process that we build, how can we justify or at least even evaluate and measure how much of these resources are used, and if not, if they're underutilized, then is there a way to ask a particular resource to help us out, right? So let's think about it. Let's talk about the memory. Start from go clockwise. So start from the memory. Can we ask the memory to help us out? Because our memory is doing nothing just like our CPU. Can we ask our memory to do something to help us out with this process? Anybody? Yeah. So
You could cache more data, that's exactly
right.
it.
So now, so instead of waking up the elephant for a little thing, we can actually buffer the data into the memory. So let's try to do that. So instead of writing to the file, I'm going to put it into a memory buffer, right? And then I'm going to basically say if count.
So basically he's going to batch up 1 million records.
Right, so this is what I'm doing in batching. So now I'm going to say,
he's going to buffer them in memory, then flip the memory buffer and write it out. By flipping, that basically makes another memory buffer available for the data that's continuing
it's actually,
to come in.
yeah, it's actually just, flipping just simply rewinds it to the beginning, and then so that's basically right, and then that's when we get to the other part.
Yep.
All right, so very simple code, right? So let's try to run this code again. So let me just see if we got everything right. Yep. And all of a sudden, you can see a very simple technique of just buffering the data that took, what, all 2-3 lines of code. And all of a sudden, I'm pretty much within my SLA. I mean, I can skip the first line because, you know, the startup time of JVM and everything else. But all of a sudden, I'm actually within my JVM, or I'm sorry, within my SLA under 2 seconds. All right? So going back to the slide deck, we've used the memory to help us out. But are we still writing data efficiently? We're writing it more efficiently, that's for sure. So we actually address a little bit of a concerns for this hard disk, right? But are we still writing the data efficiently? Because remember, as Tom said earlier, we're writing the data, we're ingesting the data for the purpose of processing it later. So at some point of time, we're going to have another problem of reading that amount of data. And again, we're going to have to figure out how to read it quick enough. And is there anything we can do on our read side to be able to process the data quickly, right? And that might actually encounter some other problems. So what can we do more? What more can we do to write the data efficiently? Compress, right?
Compress.
So again, so the compressing, but think about it this way, and you can say, well, okay, Hadoop has compression, and you know it's not a new thing. And I would never say that what we're presenting here is such a new thing. But in fact, what I was surprised is that Hadoop's been around for a while. All these problems of data ingest been around for a while. But so far, I couldn't find anything, including Flume, that could solve my problem with that particular client with the rate of ingest that I was required to support. So okay, so we can of course compress the data. So compression, what compression will give us, compression will start using our CPU because it's going to compress the data into a smaller chunk and then write it, again, a much smaller chunk than what initial data was. So now if you think about the implications on the read side, what's going to happen is that when you read, for example, a certain amount of bytes, those bytes does not anymore represent, let's say, 100 records. They represent much more of those records. So now you can read it much faster from the hard disk, and then you can expand it by using CPU. The hard disk is not doing anything for that, and then you can process. So you can achieve much quicker processing while still while operating on a compressed data. Okay, so let's try to compress the data. So what we're going to do after we flip the buffer, we're going to say compress byte stream. Into, byte array. Oh, thank you, Tom. And that we're going to do is so just a very minor change, right? But let's see what happens right now. Pretty slow, isn't it? So as soon as I added compression, you're like, okay, well, you're way past your SLA, even though you're writing less data and so on and so forth. But look at the window to the right, I guess, of you, at the bottom. What does it tell you?
We're not utilizing all threads.
I'm not utilizing all the threads. So,
that's exactly right.
So at this point of time, I'm going to just kill this process, right? And
yeah, because we don't want to go
there's
slower.
no need to, yeah, we don't want to go slow, we want to go faster, right? And at this point of time, like I said, I wanted to write this code in front of you just for you to make sure that you understand how it evolves, how easy and simple it is. The actual code that's going to do this fast ingest is written down below. It's pre-written already. And basically, the reason why I don't want to do it live is because it's a little more complicated because you want to be able to maintain a sequence. So you want to be able to distribute your compression, but then resequence it back in a proper order. So there was some queuing involved and so on and so forth. But let's run this one. So basically what I'm doing right now is saying, listen, I'm going to ask my CPU and I'm going to distribute, because my bottleneck right now is compression, right? But I have 7 more cores to play with, right? So now I'm going to be able to utilize all of them, right? And look at the performance time right now.
So now we're keeping up with the rate of data as it is produced.
We're almost keeping up with the rate of data as it produced. We're twice faster than we were when we were just writing a simple 1 record at a time, okay? And you know, so in this case, what I'm trying to say is that it's before even asking for new hardware, all we did is just really apply kind of a basic analytics or basic, a job that a typical developer should have done, and analyze what's going on and say, listen, can you go back to this slide, for example, and analyze your process within these 4 musketeers and see if everything's being exhausted before you sort of ask for a new hardware, right?
And of course, the fourth one, right, network, is all about being able to scale multiple collectors, right,
Yeah.
In parallel, and feed them with separate network feeds.
Right. And again, if you think about network, actually, I'm glad you brought it out, because if you think about the network is very close into what it's capable of doing to hard disk, because at some point of time, your network card can only pipe that much data through it. So if you're going to be either I/O bound or network bound. I always remember the joke about the infinite pipe.
Infinite pipe.
Yeah. It's an inside joke, but anyway, so there is no infinite pipe. That's the bottom line. So you always have to know that there is limitations on everything, and you basically want to do where we started, just to analyze and go back and to analyze the process. Where we started with an imbalanced process, right? So it was working. If you follow the Martin-Fowler's principle, make it work, make it right, make it fast. So we made it work. The ingest working, I was writing it out so I can start testing some reads and so on and so forth, but it was not working efficiently. So it wasn't right. It was made to work, but not made to be right, and definitely not made to be fast. So, and when you start analyzing, and so the goal is kind of to achieve this perfect or near perfect mechanical sympathy. And how many of you have familiar with the concept of a mechanical sympathy? Have you read, like you can Google it. Basically, it's the guys who created this LMAX disruptor technology, which outperforms the fastest Java queue by like 100,000 times. really that much. They've done a lot of interesting things
Very
within.
popular within the financial services space,
Yeah, and
where speed is king.
they sort of cornered that concept of mechanical sympathy because they say, well, listen, actually there's a slide for that. Like, there's many different ways to describe what mechanical sympathy is, but in my opinion, it's an ability to write software with a deep understanding of its impact or lack of impact on the hardware it's running on. And that's essentially what we did, because we were trying to analyze what's going on with our process and see if there is anything we can do within the scope of our current hardware to fix it before we start thinking about upgrading our hardware. So we want to be able to ensure that the work is balanced across all of these resources. Now, before we move on, anybody has any questions?
Please come up to the mic. Thank you.
So you're now staging the data through the DRAM, right, memory DRAM. So what happens if you lose power? Does that pose any new challenges that you didn't have when you were writing the disk?
Yeah, so the question is the high availability question. A very good question. I've been asked very often. And again, so in this particular case, I'm showing you like very light version. The actual solution includes exactly that. So there is a high availability strategy as part of the process, right? And what the high availability strategy is, it's whatever you decide it to be, however you decide to implement it. So you might, you might use some in-memory, distributed in-memory cache. You might use like a write-ahead log concept or something along those lines, maybe writing to the machine that actually does a much faster I/O but limited storage room, so you can actually delete it like a rolling log or something like that. So what we're doing, we're exposing the strategy with the custom solution, but and we provide a couple of implementations. But within our client, the HA is not actually their concern, because what they're giving us is the backed up data. So it's a little different than actually what we're showing. So in other words, if we lose something, we basically write a little acknowledgement point in a single file. So if I lose something, the acknowledgement basically will not be sent, which means that they can resend that file, that piece of data over again, right? But it's a very good question, because it's really a concern, because once you're dealing with the buffering, you're essentially creating a state. And at any point of time, the JVM crashes, that state is lost unless something was taken, it was taken care of ahead of time. Any more? All right, moving on. Oh, so we kind of got through our demos a little, not in the proper order. So we went through that particular demo. So the suitcase pattern, it's something that Tom and I have been talking about for the past sort of there's no real pattern, like you will not be able to go on Wikipedia and find it.
We're going to be setting up a little bit for our talk tomorrow.
Yeah.
So today's talk was kind of focused on ingest. And certainly, buffering and compressing is a very important part of ingest, as Oleg has shown. However, we kind of came about the suitcase pattern when we looked at the problem of query, right?
Right. And that's actually very interesting, because if you think about, and Tom mentioned it earlier in the talk, that how many are using Hadoop for just a plain storage? I expect no hands. Good. So because nobody, there's much better solutions if you just want to store data. There's much better and cheaper solutions to do that, right? So we're using Hadoop as a big processing engine that also has a storage part to that, which allows you to distribute the data itself and then send the code to process it locally. So in fact, if you think about Hadoop in general, like Hadoop is about big data. No, Hadoop is about small data. Hadoop is what allows the big data to become yet small again. Because 1 gigabyte file on 4-node cluster, it means that it's at 250 megabytes per node, right? That's what the single node has to process, right? And that's kind of what we do that's how we treat Hadoop. So when it comes to the suitcase and the suitcase pattern, is that when the ingest requirement was just only one side of the requirement that we got from the client. The second side was to do with the query. And this is really why we wanted to start getting into the smart ingest. So not only to get data there quickly, but to be able to actually use this data also quickly. So, and the suitcase, the reason why we call it the suitcase is because we were able to maintain various different strategies, whether we're using outside like Elasticsearch or whether we're doing some kind of internal indexing or dictionary approach. But what we were doing in combination with compression, what we were doing is created these suitcase files or suitcase records, which essentially what the suitcase was is the batch that was, for example, 100,000 records, right? And then some meta information in front of it. So it's kind of like a sequence files, but the key itself would be a little more complex, right? And what we're able to accomplish with that is the same kind of ability to quickly peek at the header, so to speak, find out what's there, and see if I have to even worry about that other part. And if I don't, I can just skip it because there was a byte, and not a byte, the integer field that would tell me how many bytes I can skip. So we actually did a search with that type of file on their CDR records, and out of 16,000 batches or suitcases, as you call them, on a high cardinality field like IP address, which comes in the range of anywhere between 10 to 16 million within that particular test case, we had to uncompress only 2. So basically, the entire file was skipped, never read.
Right.
So I didn't have to use the I/O, didn't have to use the CPU time. It was all done that quickly.
Yeah. So we don't unpack it unless we have got a fairly good feeling that the data we're looking for is in it.
Right. And now in my favorite part of the presentation, so what's next? So we talked about the fast ingest, we talked about the suitcase pattern and so on. But suitcase patterns kind of segue us into this, let's be smart about our ingest, let's just not worry about being fast, let's just be a little smart. So, and this is what we start thinking, that how much data is available or could be available to us during the ingest is lost after the ingest. Think about this way. Think about the fact that if you using compression and you compressed, 100 million records, right? Well, if your manager or your business tells you, how many records was there? How can you tell them that? Like if it was a plain text file, you can do WC-L and you can tell them, even if you go to the blocks and figure out that. You can do that. But when you have a compressed file, can you get information? So what would you resort to? Running a MapReduce that was just counting records? That sounds like inefficient use of resources. Would you agree? Right? So what was the original size of the file? That's something that is completely lost because what you see is the compressed size of the file, but not the original size of the file, right? So literally, how valuable is the data available to us during the ingest after the ingest is completed? And how expensive would it be to retain the data available during the ingest? And this is kind of a work in progress, and I'll give you a little preview of that. And tomorrow, when we talk about wiretap your app for knowledge, we're going to dive much deeper into this. But here's some of the samples of what available during the ingest, the data that we completely ignore and lose and destroy or not even look at. So a record count, right? Something that I just mentioned earlier. You want to count the records. Well, why don't you count them as you were processing them? Because you were processing one at a time, right? So it would take you extra 4 bytes to write it down somewhere at the header of the file, and you'd be able to always get that answer. Highest, lowest record length. You are processing the records as they come to you. So how difficult would that be to maintain that counter? Average record length, compression ratio, right? That's information that actually exists there. I call it implied or existing information. So this information is actually existing, right?
But here's the data that really gets me interested, right? So basically, if you're able to look at a batch of records and understand the unique values that are in that batch, especially for a particular column, right? You can begin to think about those batches not only as ingest batches, but as windows, right, for complex event processing. Yep. So essentially, now I can begin to look at, for example, if I'm in an industry where I'm interested in whether or not a particular field is getting an awful lot of repeats, right? Maybe this is an IP address for a system that's connecting to me, and I want to do some kind of distributed denial of service identification, right? Very simple to do that simply by looking at the windows and understanding how many times did that IP address show up in my logs over that period of time.
Right. And the interesting thing, the one that excites me from a developer's perspective, is that before compression, before any of these optimizations, what about the value encoding? Like, for example, in our records, they appear, unfortunately, I cannot show you the actual record because client considers it proprietary. But in my record, there was 3 IP addresses per record. Now, obviously, they come to me as a string. So it could be as small as 7 bytes, as large as 15 bytes. But what is an IP address, IPv4 at least? It's an int, right? So how much bytes should it really take? 4, right? So every time, even with the smallest IP address, right, with a single value per octet, I still get 7 bytes. So putting it into 4 sounds like a good idea. But when I did analysis on the sample data, I realized that the average was somewhere between 11 and 12. So that's almost 3 times just for the value encoding that takes, again, 1 line of code. Okay? So port number, how many bytes can I fit that into? I mean, it's not really short, but short from the minus, from negative to positive, fits the range of ports, right? So I can actually pack it into a short, right? Instead of, if it's a 5-digit port, then
So
it's a
rather
5
than 4
bytes,
bytes
right?
used
So
to.
instead of being 5 bytes used to, right?
Yep.
So now, if you look at some other aspects of data, there's another interesting thing about machine data, like event data or CDR data or ACH records from the banks. The interesting part about that, there is certain things that are always there. And, certain things that are actually like a reference data. Like, for example, in these particular records, one of the fields was present that there was a protocol. It was very low cardinality. There was only 8 protocols that they could be there.
TCP,
So,
UDP,
right.
FTP.
Yep. So think about the fact that, let's say, there was the longest one was ICMP echo request. That's how many bytes it would take to write that protocol, right? But if I have only 8 protocols, how much bytes do I really need to store them? 1. What if I had a reference table somewhere that 1 stands for TCP, 2 stands for UDP? So all of a sudden, you start thinking about the encoding, and now before compression, before everything, you can actually make the record smaller. Now, some records also have these formatting characters that absolutely doesn't really have to be there when they are written because, you know, you can, as long as you have a process to restore them back into that state, that's really what you need to do. So anyway, we're going to talk about more. We're going to talk more about this tomorrow during our Wiretap Your App for Knowledge, and there's going to be more demos. But I kind of want to pique your interest a little bit and run something quickly so you can understand the type of data and what you can do during the ingest to sort of pre-analyze the file. I mean, think about the concept of file that is written and is being pre-analyzed so you can get that information. So I have. I just ran a status on the file that has 100,000 records. Obviously, I didn't read the entire file because that status was pre-written, and it actually took 163 bytes to write. So let's review it. So I know exactly what the original file size was. I know exactly what the compressed size is. I know how many records was there. I know how many different record types in that file. Yeah, the low-high average, my numbers are a little off here. I just messed up the counter, I guess. But unique field values, this is important. So I call it fields for a different reason. We'll get into more details about it tomorrow. But right now, let's call that columns, right? How many unique column values does this file have? That's a pretty interesting piece of information. Would you agree, Tom?
Yeah, yeah,
So,
especially in the use case that we're going to be talking about tomorrow is one that we're doing for the banks that's looking at fraud, right?
Right.
So,
and now, the other thing is how many unique values per column, actually. So, because you can say, okay, well, I have overall I have 210,000 unique values. But how many unique values per column? You can see that in my record 1, in my column 1, I had a sequence number. It's always the same for this ingest. So there's maybe some interesting opportunity there that, you know, to do it better. This is a timestamp. I know that I can tell you right now from this number that that the 100,000 records came, in this particular case, were emulated, covered 3 seconds, right? Because you know timestamp's been updated every second. But all of a sudden, I'm scrolling to the right. Now my 11 and 12, well, all of a sudden we can see how much higher the cardinality is there. That's because this is an IP addresses and this is a port numbers, right? So all of a sudden, all the data was collected and given to you for free during the ingest. All you need to do is just not throw it away. And with that,
yeah. We've got a little bit of time left for questions. We kind of broke in the middle there, but if there are any questions here, obviously feel free to come up. Otherwise, I encourage you to visit our talk tomorrow.
Microphone?
I see that you were tracking all the unique values in certain fields of that file. So do you have to pre-sort the data as they are ingested, because you have to basically do a distinct count on it?
Yes, there was a pre-sorting was involved, but I actually do it both ways. I'm experimenting with doing it. So because sort, obviously, like everything else, will take a little time. So sorting, you don't really have to sort it, but I'll talk to you about the techniques that I'm using tomorrow. But yeah, it is a big part of it. Any more questions, guys?
All right. Thank you.
All right, thank you.